It is now my great and distinct pleasure to introduce our keynote speaker for today. Dr. Jennifer Wiseman is an astrophysicist, author, and speaker. She studies the process of star and planet formation in our galaxy using radio, optical, and infrared telescopes. She is also interested in national science policy and public science engagement. She served as Congressional Science Fellow for the American Physical Society and directs the program of the Dialogue on Science, Ethics, and Religion, DOSER, for the American Association for the Advancement of Science, the organization we mentioned earlier and we'll talk more about tomorrow. Dr. Wiseman studied physics at MIT, co-discovering comet Wiseman-Skiff in 1987, and continued in astronomy with her doctoral research at Harvard. She has worked with several international observatories and is currently a senior astrophysicist at the NASA Goddard Space Flight Center. Dr. Wiseman is a fellow of the American Scientific Affiliation, a network of Christians in science. I first had the pleasure of meeting Dr. Wiseman in 2017, where I was struck both by her sheer brilliance and her careful consideration of others. That combination has made her one of the most important voices in the dialogue between science and religion. So please, help me welcome Dr. Jennifer Wiseman to the stage.
Thank you. Thank you very much for that warm welcome. I'm so honored to be here at Eastern University, and in particular visiting Palmer Seminary here. I'll say a little bit more about that later, but we're very excited about the work that seminaries, including Palmer, are doing to bring science more into the sphere of discussion and training of future clergy, and what that will do, wonderful things that will do for congregations across the country and around the world. I am an astrophysicist, and I think, it's kind of late in the day where we're talking about right now, or at least where this is being recorded for those of you who are going to watch this later. And so I think we need to kind of liven up a little bit and look at some things in the universe and enjoy some of the majesty of what we're finding in the universe. And then we can talk a little bit about what that means. And I'm going to try to do all of that in 45 minutes. So we'll see if we can do that. We live in a universe that's active. This region you're looking at is an example of a region where stars are still forming. Stars are still coalescing out of interstellar gas and dust. And when the large stars actually turn on, the gravity pulls the gas and dust together. If there's enough pressure in the middle of this little clump of gas, then a process called fusion is ignited. And fusion takes hydrogen atoms, creates helium atoms, heavier atoms, and also releases light. And some of that light is energetic enough to actually go back into the surrounding gas, ionize the atoms there, and that creates beautiful colors of light that we can see. So this whole process is interactive. It's indicative of a universe that's not stagnant, but beautiful and active. Of course, I can't be here at Eastern without pointing out Dr. David Bradstreet, who's just an iconic figure here, and he has, of course, been very instrumental in, I think, inspiring the astronomy in a lot of places, but certainly at Eastern with the observatory here and with the things he has written. And I've put here a couple of books that he's written or contributed to, including Starstruck, which I think I am starstruck. So thank you, David. I myself did not grow up imagining myself as a scientist or even an astronomer. I grew up in rural Arkansas on a cattle ranch, and we didn't know any scientists, and we weren't anywhere near a university. But I did love nature. So these are some images. I went back to our family farm just a few days and weeks ago and took some pictures. And I think it was my early years of ambling through meadows and exploring streams and loving animals that made me a natural for science. Because you see, science is simply a study of how the natural world works. So if you love nature, then you love science, because science helps us understand how the natural world works. And that is, I think, what opened the path for me, along with the great encouragement of parents who themselves didn't get to go to college but wanted their children to be able to, of teachers, of churches. The church I grew up in didn't know much about formal science, but they did understand the wonders of creation and encouraged us to be in awe and wonder of creation, and also to be humble about our understanding of scriptures and things, so that I felt I could go into scientific investigations and to feel that that was something perfectly in line with being a person of faith. So I'm very grateful for my upbringing and the encouragement from schools, teachers, and church and family that enabled me to go on and explore a scientific career. Now, in astronomy, we use different kinds of tools to study the universe. We, of course, my favorite kind of astronomy is just using our own eyes. If you can ever find a dark place, which is harder to do these days, but if you can find a dark place and just look up, that is, to me, the most moving kind of astronomy from a personal perspective. But if you want to study things in detail and things that the human eye cannot see, you've got to have telescopes, and we use different kinds of telescopes. So what I'm displaying here are examples of the different kinds of telescopes that astronomers use. We have telescopes in space. So the one on top there is an example of a space telescope. This one is the most famous one, the Hubble Space Telescope. And it is in orbit around the Earth. If you look carefully, you'll see the surface of Earth down below it. It's only about 350 miles above the surface of the Earth. It isn't very far up. So the reason the telescope is in space is not to get it closer to what we're observing, but to get it above the Earth's atmosphere, because the atmosphere of the Earth can blur the light as it travels through our turbulent atmosphere to telescopes on the ground. It also filters out some kinds of light that we want to see. So it's greatly advantageous to have telescopes up high on mountaintops or even higher in orbit around the Earth or beyond to get clear images and clear data from deep space. There are other telescopes in space now and have been, so there's quite a fleet. They all have a different niche of what they can do. We also have telescopes on the ground. And I just mentioned the Bradstreet Observatory. There are observatories. You may have telescopes also of your own, but the bigger professional telescopes tend to be in obscure places, like in the lower left there. Those are the Keck telescopes on the top of a hopefully dormant volcano in Hawaii. And the Alma Observatory there on the lower right is not showing up. We're not getting the full bottom part of these images. So I don't know if those of you up in AV can either lift the image up a little bit or lower the screen a little bit so we can, well, then there's the table in the way. But those of you who can see through tables, you can see that on the lower right there's an image of an array of radio telescopes that are sensitive to light that our eyes cannot see, but that is very actively being emitted from galaxies and from interstellar clouds where stars are still forming. These telescopes pick up millimeter wavelength emission and sub-millimeter wavelength emission, and it's a very powerful observatory. Each of these types of telescopes and many others play a unique role in getting the full picture of what we're trying to study, whether that's galaxies or stars or planets. And so I think of it as like a symphony orchestra where you have flutes and trumpets and violins and percussion and more, each playing its own part, but all together you get the full majesty of the musical piece. Astronomers use different types of instruments to get the full understanding of what we're trying to study. Now, the Hubble telescope is unique in some ways in that astronauts have not only deployed the telescope into that low Earth orbit where it still is, but they've also returned to it several times over the past few decades to put new instruments in and repair things. And this is looking from inside the space shuttle. that an astronaut on the last servicing mission to the Hubble telescope took this picture. And you can see out the window there the Hubble telescope, which is in the payload bay at that moment of the space shuttle, as they spent several days orbiting along with the telescope to do repairs. This was back in 2009. But in front there is a model of Galileo's telescope from 400 years ago. This astronaut, John Grunsfeld, took this model of Galileo's telescope up with him on the flight. And here you can see in juxtaposition Galileo's telescope and the Hubble telescope. And it was, Galileo being a pioneer of looking at things in the night sky with a telescope and making recorded observations of it that launched, I think, this very serious progression of the development of optics and technology to the point where we now have things like the Hubble Space Telescope. So here's an example of how building on technologies, building on human curiosity, can open new vistas of understanding, and that feeds into the other explorations of humanity, science, of course, but questions of theology and philosophy and our expressions of art and music. So here's how technology can advance and actually open our eyes, our minds, and our hearts. With technologies like that, we are getting images like this. So here's another one of these. Happens to be my favorite. Star-forming regions where there's a cluster of massive stars that have formed cosmically recently, and they are impacting the surrounding environment where winds from the stars are carving out these pillar-like structures and eventually will blow most of that leftover gas and dust away. And the light from these massive stars is ionizing the gas and making it glow in these beautiful colors. We say as astronomers, oh, when we see these nebulae, they're beautiful. And we also say, oh, this is indicative of activity, that stars are still forming. So we live in an incredible universe that inspires wonder and awe. And I'm so glad. And we have to ask ourselves, why and what does that mean? What should we do with those feelings? Here's another image that I'd like to point out. This is a cluster of stars. This is the core of what we call a globular cluster, which is a very crowded region of stars. The stars are held near each other by their mutual gravity. They don't collapse together because they also have some of their own independent velocities, so that kind of balances out. But you have this kind of gravitationally bound group of moving stars. And if you were to look at this globular cluster from a telescope on the ground, most of the time the light would be kind of blended together because because you can't resolve or see the independent stars. You get that blurring of the light coming through the Earth's atmosphere. But in this case, the image is taken from a telescope in space, and you can actually differentiate, because you have that sharp resolution, you can actually differentiate star from star and see the differences. And you can see that there are many, many stars in this cluster, and you can also see that the stars are not the same. Some of them seem to be brighter than others. Some are different colors, reds, blues, yellows. This indicates different surface temperatures of these kinds of stars. And you can even see lots of smaller whitish greenish stars. If our sun were in a cluster like this, it would be like one of those smaller whitish greenish stars. So you can see just visually that stars are not the same. And there's a New Testament verse that says star differs from star in splendor. So you get extra credit if you find out where that's stated in the New Testament. But we have an amazing technique now, or technology, to enable us to see this kind of majesty in the stars. And we can also see it in context. So now I'm pulling out using a telescope from the ground that gets a wider field of view than the Hubble telescope, and many telescopes get small fields of view in great detail. This telescope is looking at a wider field of view, looking toward the center of our galaxy, where you see a lot of stars and a lot of dust, as you see in that kind of lower left quadrant. And some of those bright star-like looking things are actually clusters of stars. And so we're going to zoom in now from this wide field of view and go down and look at one of those objects and see what happens here. So, whoops, that's not, there we go. Let's see if I can get it. There we go. So here's this constellation Centaurus. We're zooming in now and transitioning to an image taken from telescopes on the ground. From telescopes on the ground to telescopes in space. And now you can see the Hubble image in all its detail. And I think that is putting something in context really helps not only the wow factor, but kind of seeing how things fit together. I'm going to do that again if you like, so we can kind of see the big picture moving to the small picture. So here's that violent constellation, Centaurus, moving in, zooming in to one of these objects, which we can now see is actually a cluster of stars, a globular cluster. And then we'll transition over to the Hubble image, which sees the detail, and we can actually see some of the individual stars. So that, I think, is another telling example of what technology can do for us. It opens our eyes both to the big picture and also to the details of what's going on inside some of these regions that in detail that we would not otherwise be able to see. This is the Orion Nebula, another one of these star-forming regions. It's near and dear to my heart because this is what I studied for my own doctoral research. But I didn't look at this lit-up region where these massive stars have already turned on and they're lighting up the surrounding gas. I looked kind of through this nebula with radio telescopes to the darker gas behind it, which is invisible in visible light, but it's quite bright in infrared light and in radio light. And it shows us examples of protostars, stars that have not turned on yet, but are still coalescing, gas is falling in, it's heating up, and they will eventually become stars. But in this foreground nebula, as you look here with this image from the Hubble telescope, you see the bright stars, but if you look closely, you can also see some smaller stars, and I'm going to blow them up here. So we have a couple of examples here of smaller stars that are trying to form. It takes longer for smaller stars to form than the big massive stars take. And here you can see a couple of these young stellar objects, and around them you see these dark regions. They're disky-like regions. You can see in the lower left one that's kind of face-on toward us in orientation, and in the upper right one that's kind of edge-on. These dusty disks around these young stars or young stellar objects trying to form are about the diameter of our solar system. And so we are now discovering that most stars in our cosmic era that are form with these dusty disks of material and debris, like dust and small solid particulates around them. And it's in these regions where planets form, and they're coalescing as the star is forming. Planetary systems form along with stars, and as you heard earlier, we now know that it seems that planets are quite common around all stars in our galaxy. Here's an example of such a planetary system. This is an artist's conception of a real system of a star, not our sun. In this case, the star has 6 planets that are in tight orbits around that star. Now, we can't get lovely images like this very easily because the way we find most of these small, dim exoplanets is indirectly. Many of them are detected when they orbit in front of their parent star, and the brightness of that star appears to dim a little bit because part of it's being blocked out. So those transits or those eclipses are what let us know that there's a planet around that star, and we can also study something about the atmosphere of that exoplanet as the starlight comes through the outer regions of that planet's atmosphere to our telescope. But we are now at the point of characterizing some of these exoplanets. An exoplanet means a planet outside our solar system, Which is quite exciting, because when I started graduate school, we didn't know of any planets outside of our solar system, and now we know of thousands, and we can do the statistics, the extrapolation to know that most stars have planets, and a lot of those planetary systems are going to include planets that are in temperate zones around their parent star and could harbor liquid water. We are also exploring our solar system using probes. So I think you're all familiar with the Perseverance rover. Here's a nice picture of Perseverance, but here's a nice picture from Perseverance of the Martian surface. So if it's relatively near to Earth, we can study our solar system not only with telescopes, but with probes and even with people. We're preparing to send people back to the moon and on to Mars. So that's a quite exciting way as well. Outside of our galaxy, which contains hundreds of billions of stars and their planets, we have other galaxies. Now, we can't get far enough out of our own Milky Way to take a picture, to take a selfie, but we can tell that it looks kind of like this. We live in a spiral galaxy with spiral arms, but this is another spiral galaxy. It's one that I find particularly beautiful, but it's somewhat randomly chosen out of the archive of images that we have. So you can see what a spiral galaxy looks like. If you look closely, you'll see other galaxies in the background of this image. There are so many stars that the starlight kind of blends together as we look from this distance, and in the middle, the glow from so many stars is apparent. And we now know that in the core of most galaxies, there seems to be something massive and very compact. So we would call it a supermassive black hole. We can't see the black hole directly, but we can see the material around it telling us that there's a black hole there. We now know that galaxies are interactive, especially in the early universe. I think that's one of the tremendous findings in recent decades in astronomy, is the fact that galaxies are not always isolated, that throughout the history of the universe, galaxies, including our own, have been drawn together with other galaxies to build bigger galaxies. Now, most galaxies are caught up in the expansion of space so that they're moving apart from each other, but if any of them are actually close enough so that their mutual gravitational tug is strong enough that it can dominate over that tendency to move apart from each other, they will merge. And so here's a pair that's in the process of merging. Here's another pair that's farther along in that process, and what happens is that the turbulence of this collision of galaxies can stir up the gas, and stirring up the gas can actually stir up more bursts of star formation. So if you look and see those bright regions around what's left of the spiral arms, those are those nebulae, but in these other galaxies where stars have been incited to form through the pressure against these gas clouds and the collapse in these little modules of gas within those clouds, turning on new stars, providing brilliance. If you think this is all kind of esoteric, our own Milky Way is on a head-on collision course with the Andromeda Galaxy, which is our nearest neighbor big spiral. So we will be experiencing something kind of like this in about 4 billion years. So you should start preparing now. Models show that most of the individual stars in here, as you heard earlier, space is mostly empty. Even in these galaxies, there's a lot of empty space, or at least space with very low density gas. And so most of the individual stars are not disturbed, but the shape of the galaxy as a whole can be greatly perturbed, and certainly the population of stars that are forming there. And we now know that there are, in fact, hundreds of billions of galaxies, and each of these galaxies contain hundreds of billions of stars. And so, you have to do math with a lot of zeros to figure out how many stars, and if these stars have planets, how many planets there must be in the universe. Here's just an example of one of the kind of deeper fields that we take with telescopes like the Hubble telescope, and you can see different kinds of galaxies. And if you imagine this extrapolated over the whole sky, so this is just like a little soda straw area of the sky, looking through a drinking straw. And this is what you see, and it kind of looks similar no matter which direction you look in the sky. And so just imagine this extrapolated over the whole sky. This is the universe that we live in, and we're not in the center. You know, we could go out to one of these other galaxies and look back, and our Milky Way would look like one of these other galaxies. So we have a sense of wonder and awe. In fact, Immanuel Kant said, and this is on his tombstone, I understand, translated here into English, into this quote, that two things fill his mind with ever-increasing wonder and awe the more often and the more intensely he reflected on them, the starry heavens above him and the moral law within him. And that's kind of interesting. You know, here we have the idea that the wonders of nature can inspire awe, and the reflections on the moral law, justice, things within us, can also inspire a sense of wonder and awe. Where does this come from? It's these kinds of questions that actually drew C.S. Lewis in his adulthood into eventually becoming a Christian, was wondering where the moral law comes from, that everyone seems to believe there is, even though it comes out in different flavors in different cultures. I want to take just a little aside from the astronomy briefly. Well, it will include astronomy, but broaden the discussion to talk about how new technologies enable new discoveries and advances. Because some of you watching this may say, well, this is great, and I'm really fascinated by the night sky, but it has nothing to do with my work. And if you are a seminary professor or a seminary student, you might be saying, well, this is all nice, but it has nothing to do with, really, with what I'm going to be dedicating my life to now or in the future, or for my future congregation that I may be leading. Wrong. All right, so new scientific understanding actually spawns new questions and brings new depth to old questions. And science and technology impact nearly everything about life today. So this is why seminaries like Palmer, who are on the ball, need to incorporate discussions of science and technology, good science, forefront science, the science that's actually happened, mainstream science, into discussions of how it impacts people's lives and how faith communities can incorporate that knowledge into their ministries and service. So science and technology impact our lives in both philosophical ways and very practical ways. And so these are just examples, and you can think of more, and each one of these we could have a whole symposium on. But food and agriculture, how our food is produced, communications, our environment, including climate change and other environmental challenges. Health issues, obviously, the pandemic has opened up a true understanding of how science and technology impact and intersect with human health. Space exploration, education, animals, how we relate to animals. Are they, and what are animals? Are they just food, or are they our peers? Can we use them as lab equipment, or do they have rights and needs of their own? How do we interrelate with them? Defense, the arts, literature, history, and social justice intertwines with all of these areas, and social injustice, I should say, as well, and how science and technology are used, can be used, and have been used, and more. So science and technology affects every part of our lives, whether we realize it, think about it, or not. And so it is important to think about it, to employ what we understand in ways that are actually beneficial. Science and technology are also advancing, and these are opening up new questions about who we are. What does it mean to be human? How do these discoveries affect our view of ourselves and change it and cause us to be challenged? Here's a few ways. These are some broad examples. Each one could invite a whole symposium on its own right, but I just want to get you thinking broadly. I've already mentioned that we're discovering a lot of planets outside our solar system, exoplanets. And a whole new field of science is opening up called astrobiology, where we are bringing together what may have been disparate fields of science to inform how we're going to study these exoplanets and how we're going to determine whether or not they might be habitable for life or might even harbor even simple life. Astronomy, physics, geology, chemistry, biology, many more sciences. The question has been out there a long time, are there other planets in the universe beyond the planets in our own solar system? We know the answer to that now is yes. Then, of course, the question that follows is there another Earth-like planet out there? Is there life beyond Earth? Those are alive questions. We haven't found life beyond planet Earth yet, but we're in an age where we are now setting ourselves up to be able to answer whether there are planets that are showing biosignatures, signs in their atmospheres of biological activity. And it could be relatively close. I mean, we're now finding that exoplanets are common. Even the nearest star system to our sun, Alpha Centauri, one of the stars in that system called Proxima Centauri, which is the tiny little one in the lower right there, is the closest star to our sun, and it has a planet that could be temperate in its temperature. We're wondering which planets could have water. This is an artist's concept because we don't yet have the technology to take this kind of spectacular image, so we're imagining what it might look like on Proxima Centauri. But we're in an age where within the lifetime of some of you watching this, we may be able to answer at least whether there are planets that are habitable or are showing even signs of having biological activity. And we can tell what fraction of stars actually have potentially Earth-like planets. We have to look at things. If we look back at Earth, we could tell that there's life here by seeing evidence of oxygen being replenished in our atmosphere by photosynthesis. We have liquid water that can help support life. We have reflected light that shows evidence of life. We even have methane being refreshed in our atmosphere largely because of cows, and so we might find a bovine planet somewhere when we see methane in its atmosphere. We look for these kinds of things on other planets because we can't travel there yet. We don't have the technology to travel to these exoplanets, but we can observe them from distant telescopes and look at their atmospheric composition, see what's in the atmosphere, and see if it matches signatures for biological activity and rule out other explanations. So we might be doing that, within the next certainly we're already finding the exoplanets. We're already starting to do some of the preliminary analysis of some of them. The next generation of telescopes will be able to do even more analysis of the atmospheres of Earth-sized planets that might harbor conditions we think are needed for life. If we find biosignatures, even just for simple life, astronomers would be thrilled if we found evidence for bacteria or something like that. Are we prepared for that philosophically? What does that do to our view of ourselves as humans? Okay. Here's another thing that's changed. We found out that we have something called the microbiome in our bodies, that our bodies are full of other organisms. Now, you kind of already know that, but think about it this way. There are at least as many organisms or cells in your body that are not you, that have different DNA, as you have cells that have your DNA. And you need this biological community working within you to live. So what are you? Are you an individual, or are you and I each a walking community? That's a philosophical question. It's also a practical question when it comes to nutrition and healthcare and how we use pharmaceuticals. If we mess up our microbiome, we're messing up our health, our sense of well-being. Turns out that your mental health is connected to your gut health and things like that. What about the human-machine interface? The lines are blurring between what's a human and what's a machine. It used to be that it was a clearly differentiated thing. Of course, now we're all staring at our smartphones, so we kind of know we're starting to merge. But there's even more serious merging of humans and things created to either help us in ways where our bodies are not functioning well, or to enhance us beyond what naturally our bodies would be able to do. Is that okay? Is that an okay thing to do? Lots of ethical questions there. Advances in neuroscience. We're learning about the brain more and more, but am I only my brain? You know, what does that tell us about humans? Am I responsible for my actions, or is my brain basically dictating how I act, and am I responsible for my brain chemistry? There's questions there. And how do you know when you're alive or dead? There have been some recent studies where an animal was thought to be dead because it had no more brain waves, and then it was brought back into functioning again. So how do you define when something is alive or dead? Not clear. What about genetics? Certainly we've had huge advances in genetics and in mapping the genome of humans and other creatures, but are we defined by our genes? How much of us is dictated by our genetic makeup, and how much is shaped by our environment? Very interesting questions. And then the ethical questions of, should we edit our genes and our genome? Certainly there's great promise for eradicating terrible diseases if we can edit them out of the genes, but there's also great ethical dangers in editing human genome, especially if it's inherited beyond the original editing. So this is what CRISPR technology brings to us, both promise and challenge. Technologies do transform biology, as the cover of Science magazine says here. But it also can prevent profound ethical challenges. So here's Francis Collins, the head of the National Institutes of Health, who is normally a pretty mild-mannered kind of person, and he's also a Christian and has written a book called The Language of God, which is a marvelously moving book. But he was horrified when there was a gene editing episode in China where the genes of two embryos were modified, presumably to protect them from HIV, but when you modify one part of the genome, you don't know yet how it's going to modify other parts of the person. And if you move out ahead with the technology before we know all of the impacts and before we can actually contemplate the ethical issues that may come out of it, there are big problems. And so he says regarding this particular study that it was an epic science misadventure, profoundly unfortunate, ill-considered, flouted international ethical norms, largely carried out in secret with utterly unconvincing justification. So we have an issue when technology runs ahead of both understanding the long-term ramifications of what we can do and the ethical questions of what we should do and what we shouldn't do. These kinds of things need to go hand in hand, but often do not. All right, and then there's artificial intelligence and social justice and science. These go hand in hand as well. Artificial intelligence, of course, is moving ahead at a very rapid pace. I would commend to you Nate Matthias's work on artificial intelligence in Christian thought and practice, and how we should think about it. The classical example is, if you have a self-driving car and it's coming up against choosing between missing a crowd of people to hit one person or missing one person to hit a crowd, what's it going to choose? So how do you program ethical dilemmas and morality into artificial intelligence kinds of issues? And of course, nothing is completely objective, right? Technology is developed by humans. Humans are brought up in cultures. And so we're finding that actually what's supposed to be objective, neutral technology and software and analyses and so forth are not neutral at all, because even though those who created it had perhaps no intention of putting biases into their programming and software, they're there because people come from cultures and biases that they don't even realize. And so I commend to you Dr. Ruha Benjamin's book and work. The book is called Race After Technology, figuring out that actually some of the technologies that are being used widely for healthcare and all kinds of things have embedded in them certain cultural biases that have come into the whole system of technology development. We need to examine what those biases are, what the human impacts are in the technologies and the software that we're using across, and that's growing in use across cultures around the world, and try to address this as best we can. All right, and then there's environmental stewardship and how we understand our changing planet and respond to it. So these are issues. I just wanted to point out that science and technology affect so many aspects of human life, and it's so important for people in faith communities to be aware, to be part of the conversation in a very constructive and informed way. There's also great opportunity. It's not negative. It's not all threats. There's great opportunities for using science and technology to the great benefit of humanity and other creatures. I pulled this headline out of the New York Times from a person who wrote an article about her own conservative faith meshing with her view of environmental stewardship as being part of that. So can science and theology come to complementary conclusions? They're answering different kinds of questions, but of course I would say yes. And let me just mention a little bit that the American Association for the Advancement of Science, which is a scientific society advancing science for the benefit of all people, has as one of its programs, as you've already heard, this dialogue on science, ethics, and religion, facilitating communication and engagement between scientific and religious communities. And it's this DOSER program that is sponsoring, as one project, the Science for Seminaries work, of which Palmer Seminary is playing a part, and we're so grateful for that. You can learn about DOSER program at this website, AAAS.org/DOSER, and we have resources at sciencereligiondialogue.org, including a great little short film series that's wonderful for discussion starters in classrooms, seminaries, and other discussion groups. Dr. Edelman, who's a professor of psychology at Catholic U, says scientists and people of faith speak a common language which is awe and wonder about the world at large. So let's meet on common ground and consider our common interests. I like that. All right, so there's a little bit more. We're very active on social media. All right, all these challenges are very interconnected. The science and technology is interacting with economics, which interacts with government policy and law and business and education and international relations and the environment. So people in all different fields need to be talking and working together as we face both the technological challenges, ethical challenges, and the promise of using technology and science well into the future. All right. Last example here, and this is bringing us back to the astronomy. How is this changing our view of ourselves? Well, the whole universe is, in fact, developing and changing. We've learned that very much so over the last few decades with astronomy. And here's another image of galaxies. This is one of my favorites, the Hubble Ultra Deep Field, which is, again, showing you a field of galaxies taken by just pointing the telescope, the Hubble telescope, in a direction where there weren't very many nearby stars to drown out the image, and collecting light for several days to see what faint things would show up. And so all these little blips of light here, these are not stars. There's a couple of little foreground stars in here that are from our own galaxy, but all the other blips of light, large and small, are other galaxies, each with billions, sometimes hundreds of billions of stars. And again, imagine this extrapolated over the whole sky. This is the kind of universe that we live in. And not all of these galaxies are at the same distance, right? Some of them are closer to us, some of them are farther away, and it's taken longer for the light from the more distant galaxies to get to us than the light from the more nearby galaxies. So, this creates a kind of a time machine. Of course, anything in astronomy is a time machine. Anything we look at, we're looking at it as it was when the light began its journey to us. So even in the solar system, if we look at the sun, which you should never do with your bare eyes, we're looking at it as it was a few minutes ago. And then the outer planets longer. So we have a time machine inherent in astronomy. When you start looking at other stars, we start talking about light years, which is a light year is the distance light travels in a year. and the nearest star is a few light years away from us. If we're looking at other galaxies, we're talking sometimes millions of light years away, and sometimes billions. So as we're moving out here through this deep field, you're seeing the galaxies as they were farther back in time, and you can see they start looking different. They're smaller, they're less well organized, they're ratty, and you're seeing fewer of them. That does not mean that there's actually fewer galaxies back in the early universe, but it means that we're not seeing as many of them because the light from many of those galaxies is traveling through expanding space, and by the time it gets to us, its energy has been, or its light wavelength has been stretched into reddened bands, which make it impossible for the Hubble telescope to see. We're looking for the infrared Webb Space Telescope to be launched later next year to see some of those galaxies. So here is another way of looking at this. The deep field there in the background is what you've seen before. But in those circles, we've pulled out some of these galaxies and lined them up by their distances. And measuring the distances is not easy, but you can actually see the nearby galaxies are put in those circles on the left, and the more distant galaxies are put in the circles on the right. And you can actually see how galaxies have changed over time. The galaxies on the right, again, it's taken billions of years for the light to get to us from them. We're seeing them as they were in the early universe, and they are smaller. They haven't yet formed these beautiful spiral structures. As we move toward more contemporary cosmic time, we see galaxies more like our own Milky Way. They've merged with other galaxies throughout the history of the cosmos. They have had time to get bigger. Some of them have taken on these spiral structures. And if you could look at the composition in these galaxies and their stars, again, each of these has billions, sometimes hundreds of billions of stars. The stars within them have heavier elements, and the gas between the stars has heavier elements because previous generations of stars have, through their fusion process, created things beyond the simple hydrogen and helium that was in the early universe. They have carbon and iron and nitrogen and oxygen and things that we need for solids like planets and things that we need to support life. So our own sun and solar system is not a first-generation star. We're taking advantage of previous generations of stars in the Milky Way that have produced those heavier elements that have allowed our own sun and the planetary system around it to form. So we can actually see through the time machine of astronomy that our universe has developed over time, and it continues to mature and change with the production of stars and heavier elements and planets, and this provides conditions needed for life to thrive on at least one planet. So question, does this indicate purpose? Does the universe have a purpose? Is this showing us a purposeful history of the universe? I have moved from a science question to a philosophical and even perhaps a theological question. So here's how a science question begs deeper questions beyond the science. Now, given the time, you'll have to invite me back sometime to go more into this. But I just want to point out that while scholars of the world may agree, for the most part, on the scientific picture I just gave you, they do not agree on the answer to the philosophical question. Is there a purpose for the universe? What should we make of this history of the universe and its projected future, which, if you look at the science alone, isn't all that cheery? This scientist says no, Professor John Hott says yes, Jane Goodall says certainly, and it's killing me that I can't go into this, but if you find the full essays on how these scholars were asked this question, there was a whole group of them through the Templeton Foundation, you can find it at bigquestionsonline.com in the archive. They explain why they came to such an answer. Jane Goodall says, science typically scoffs at a belief in God and tells us that we just have a God gene, and that tendency toward belief is simply part of our biological makeup. And yet we still have to ask why. Why are we programmed to believe in a God? And why are the laws of physics designed to make life ever more complex? Where did those laws come from? So there are different philosophical ways of addressing this. All right, I'm going to do something very painful, but that is to whiz through to the end of my presentation so that we can at least have 5 minutes for Q&A. I do commend to you this book by Dennis Alexander, a biologist who has directed the Faraday Institute for Science and Religion in the UK. And he addresses this question from the biologist's point of view: is there purpose in biology? All right, isn't that painful? Here we go. I will say that Jill Tarter, who's the scientist for whom the movie Contact was based upon her quest looking for life beyond Earth, but she points out this amazing thing that we are actually made of stardust. We're not just observers of the universe. We are part and parcel interconnecting with the universe. The iron in our blood was created from a star that blew up 8 billion years ago. The iron in our left hand from another star. We are the laws of chemistry and physics as they've played out here on Earth, and we're learning now that planets are as common as stars. So we're interactive. Our bodies are evidence of interaction of a universe that has changed, evolved, if you will, over time, making life that we enjoy possible. And now I want to speak, as Palmer Seminary addresses this question from a Christian perspective, and that is my own personal perspective as well. Think about the majesty of this in terms of what we call the incarnation. For Christians, believe that God is responsible for the universe, but that God is also the Word made flesh in Jesus Christ, made manifest in Jesus on planet Earth. And so we have the manifestation of God in Jesus Christ in a body that has cells that is actually connected with the processes of stars and the history of the whole universe. There's something amazing about the Word made flesh interacting with the whole universe, and that Word also upholding the universe. Lots to contemplate there. And I love this beautiful, majestic piece in the book of Colossians about this Word of God holding all things together. And Jesus himself saying that it's not just about the physical laws, it's not just about the science, although at that time they didn't talk about science. It's about a person saying, I have come that they may have life and have it to the full. And we also think about love. We don't hear that word much when we talk about science, but we should. How does love shape how we view the creation, why we work in science, what science we do, how we do it, and who benefits from it, and how and why we share it? And that should be, I think, a topic of discussion when we talk about science and religion, science and faith. Where does love fit into all of this? All right, so I hope you've enjoyed this discussion. I hope you've been inspired by it, and I hope that this conversation inspires a lot more conversations, and I thank you very much for your attention today.
Dr. Wiseman.
Yes.
So when you figured out your interest in all your work in the creation of the universe and the forms of religion, how did you come across your perspective on how it came to be and your belief on the universe combined with religion?
Well, that's a good question. So I think for me personally, I grew up in a kind of faith-based environment, and then I would, have considered myself a Christian believer since childhood. And so then, and as I mentioned earlier, studying the natural world was a natural part of my interest. I enjoy animals, plants, stars. Science kind of facilitated that study of the natural world. And I feel that studying the details of the natural world is really a way of living out one's faith. And since biblical faith, at least, says that the entire universe, everything, is the responsibility of God. If you believe that, then studying anything, including the history, the vast time and space of the universe, the content of the universe, the activity of the universe, is something that would honor God. You know, pursuing this kind of truth is something that should honor God, and that doesn't mean that there aren't disagreements and there aren't those kinds of things. But I think that the study of science is a great gift to give us more detail about the workings of nature, both to just give us a sense of awe and wonder, but also to give us the ability to serve others better. And I also think that the Bible gives us wonderful and helpful and crucial information about the nature of God, the nature of humans, the nature of how we need one another and we need a relationship with God. But it's not a great collection of books to use for science. Science wasn't even invented when the books of Scripture were put together. Likewise, the books of science are not meant, and the methods of science are not meant to address these bigger, perhaps more important theological, philosophical questions. So we have to use the right tool to answer the right question. So to me, science is a wonderful gift that enables us to understand more deeply the nature of the natural world, and that gives me a deeper respect for its creator. So that's how I would view it. So,
Okay,
thank you.
thank you.
Thank you.